Hello everyone, welcome to today's GATE section. I am Hima, Assistant Professor, Department of Information Technology, S.A. Engineering College. And today I am going to discuss about the topic tree data structure. So this is a definition of a tree data structure. It's a non-linear data structure in which a collection of elements known as nodes are interconnected to each other via edges such that there exists exactly one path between any two nodes. So that means that the data in a tree data structure are not stored linearly or sequentially. Instead, it has been stored across multiple levels, which forms a hierarchical structure, and it maintains a parent-child relationship. So if you see this sample tree, there are circles and arrows. Circle represents the nodes and arrows represents the relationship among the nodes. Now these are two examples for tree data structure. The first one represents an organization chart where the first node is the president of the organization. Then it is divided into two nodes. Under president there are two nodes. One is the vice president personnel and one is the other one is the vice president marketing. Then below that again there are two nodes. This is a director customer relation and director sales. So likewise we can continue towards downwards, and we can represent the complete organization structure using a tree. Now coming to the next example, expression tree, where we can see the nodes represents operators or operands or datas. Okay, so we can represent an expression using this tree. So here there's a simple expression has been represented, 3 into 2 plus 5. So like that we can represent complex expression also using tree data structure. Now we'll see some basic terminologies in tree data structure. So here we have a tree and there are two nodes marked as U and V. There is an edge from U to V, which means that U is the parent of V and V is the child of U. And also there is a node without parent. This specific node is known as the root of the tree. And there are a set of nodes which doesn't have any child nodes. So such kind of nodes are known as leaf nodes. Now other term is internal nodes. So we know the nodes without child nodes, they are known as leaves. All the other nodes other than the leaf nodes are called the internal nodes. Then other terminologies are like siblings, ancestor and descendant. If you see this tree, U is the root node and these are the child or leaf nodes in this particular tree, and there are two child nodes for U, V and W. So V and W belongs to same parent U. So we can say that V and W are siblings. Now ancestor means any node on the path from root to a given node, excluding the node itself. So we consider the node X, then V and U are the ancestors of X. If you are considering the node U, V and X are the descendants of node U. Next term is subtree. So here we have a tree with the name T. So subtree is any node together with all its descendants. So this part you can consider as a subtree. So it is separately drawn here with the root V. With the root V it forms a subtree. V and all its descendant nodes forms a subtree. And the term is level of a node. So level of a node is the number of edges in the path from the root to that node. So the root is at level 0. So this is root is at level 0, and the next level the child nodes of root, which is at level 1, then level 2 and level 3. So if you consider the node N, that belongs to level 2. Now height of the tree is the maximum level among all its nodes. So maximum level is 3. So height of this tree is 3. Now we'll see the types of tree data structure. So based on the number of children, tree can be classified into 3 groups: binary, ternary and n-ary tree. So binary tree means every node will have at most 2 children, Whereas ternary tree means every node will have at most 3 children, and n-ary tree means every node will have at most n children. So we'll see that in detail. So binary tree, as I said, every node will have either 0, 1 or 2, that is at most 2 children. So see this example, if you take any node 2, it is having 2 child nodes. They are known as left child and right child. And if you consider the node 6, it doesn't have any child node, it's a leaf node. And if you consider the node 1, it is having 2 child node, left child is 2 and right child is 3. Such kind of trees are called binary tree. Next is ternary tree, where every node will have at most 3 children. So if you see this tree, you can see, if you take node 5, it is having 3 child nodes. They will be known as left child, mid child and right child. Next is n-ary tree or generic tree, where every node will have n number of nodes at most. So if you see this example, if you consider the node 1, which is having 5 child nodes. So here n equal to 5. This is an n-ary tree with n equal to 5. Every node will have at most 5 child nodes. Now we'll see binary tree data structure in detail. So binary tree data structure, binary tree can be represented using an array or a linked list. So if you take a particular node, it will have 3 parts: the data, the left pointer and the right pointer. It can be represented like this. Here it is a root node which is having 3 parts: the data, then the pointer to the left child and the pointer to the right child. And these two are the left child and right child of the root, and they are also the leaf nodes. So they don't have any branches. So this left child and left pointer and right pointer of this node will be set to null, since there is no more child nodes. Now the properties of binary tree. So these are some properties of binary tree, where the maximum number of nodes at level L of a binary tree is 2 power L. Second property is the maximum number of nodes in a binary tree of height h is 2 power h plus 1 minus 1. Third property is total number of leaf nodes in a binary tree, which is equal to total number of nodes with 2 children plus 1. Next one is in a binary tree with n nodes, the minimum possible height or the minimum number of levels is log to n. And last one is a binary tree with L leaves has at least log 2 L plus 1 levels. Next we will see the different types of binary trees. First one is called a balanced binary tree. A balanced binary tree can be defined as a binary tree that has at most one difference between its left and right subtree heights for each node in the tree. That means so if you see this example, if you take this node 11, this is the left subtree, this is the left subtree and this is the right subtree. So height of left subtree is 2 and height of right subtree is 3, and the difference between these two is actually 1. So that is the condition for a balanced tree. If you consider any node in this tree, for example if you are considering node 15, the height of left subtree is 1, height of right subtree is 2, and the difference is only 1. So if this condition satisfies for all the nodes in a binary tree, such a binary tree is known as a balanced binary tree. Next is a complete binary tree. A complete binary tree is a binary tree that has all levels full of nodes except the last level, which can also be full or filled from left to right. So see this example where the 11 is the root node and this is at level 0. This is at level 0 and this is at level 1. 2 and 3. So if you see the level 0 root is filled, and level 1 these two nodes are, that is the two child nodes of roots are filled. Then next level also completely filled. Then next level is it started filling from left side 2, 4, 8. So we can say that this is a complete binary tree, and the property of a complete binary tree is it is also balanced tree. Next is called full binary tree. The full binary tree is a kind of tree where each node has either 0 or 2 children. So this is the example. If you take any node, it will have either 0 child or 2 child nodes. So 15 if you are taking, it is having 2 child nodes. If you are taking 12, it is having 0 child nodes. So every node should satisfy this condition, then it will be known as a full binary tree. Next is a perfect binary tree that has all leaf nodes on the same level, which means that all levels are full of nodes and all internal nodes have 2 child nodes. Okay, if you see this example, it is a completely filled tree. It looks like a completely filled tree. That is, all the nodes have 2 child nodes except the leaf nodes. And the property of a perfect binary tree is that it is perfect, full, balanced and complete binary tree. So those are the different types of binary tree data structure. Next is operations on binary tree. So the main operations that can be performed on a binary tree are traversal, search, insertion and deletion. Traversal means visiting each node in a binary tree exactly once in some specific order. That is called tree traversal. The next operation is searching. That is, we can search a particular data whether it is present or not inside the tree. The next one is we can insert a new node to a tree. Like that, we can delete an existing node from the tree. Now we will look into binary tree traversal in detail. So tree traversal means visiting each and every node in the tree exactly once in some specific order. So that order will be different for different types of traversals. So we have 3 orders or 3 types of traversals: in-order traversal, pre-order traversal and post-order traversal. First one is in-order binary tree traversal. In in-order binary tree traversal, we will be maintaining this order. If you are taking a particular node, left node, then right. That is the order in which the nodes has to be visited. So if you want to do in-order traversal of a tree, then first recursive in-order traversal of left subtree, then visit the root node, then recursive in-order traversal of the right subtree we will do. That will complete the in-order traversal of the tree. So if you see this example, here the root is represented as R. So the thing is, we have to start from the left subtree, root, right subtree. So it will be like this. If you come to the left subtree, this is the left subtree and this is the right subtree. See, we have to do the recursive in-order traversal of left subtree, then root, then the right subtree. So here the left node is C. So the traversal, the first node start with C, then its root node A, then its right child D. That is what? CAD. That completes the in-order traversal of the left subtree. Now we will move on to R, that is the root of the tree. Now we will move on to right subtree and we will do the recursive in-order traversal of the right subtree. Okay, so it starts with the left node again. So first it will visit E, then it will go to its root node B, then it will go this way and again left G and finally its root node F. So this is the complete in-order traversal of this particular tree. Next is pre-order traversal, pre-order binary tree traversal, where this is the order that is to be carried out, or that is to be followed, root, left and right. So first we will visit the root node, then we will go to left subtree recursively, then we'll go to right subtree recursively. We'll see one example. So here again the root node is represented as R, and we'll start with the root node. So first itself root node will be visited, then the left subtree, then right subtree. That is the order of pre-order traversal. So from the left subtree, first again it will choose the root, that is A, then its left child C, then its right child D. So that completes the left subtree. Now we'll go to right subtree. In the right subtree again we'll start with the root, that is B, then its left child E, then its right child's left node, that is what? The final EF G. So this is the pre-order traversal of this particular tree. And finally we are having the post-order binary tree traversal, where the order of visiting node is left, right and root. So first we will do the recursive post-order traversal of left subtree, then we will do the recursive post-order traversal of right subtree, and finally we will visit the root node. So this is one example. Here this is the root node, and again this is the left subtree, this is the right subtree. So we'll start with left subtree, then right subtree, finally the root. That is the order for post order traversal. So here we will visit the left node C, then right node D, its parent A, that completes the left subtree. Then we will move on to the right subtree, where we'll start with E, then again the left G, then next is its parent F, then its parent B, and finally this is the root node. So this is the this traversal is known as post order binary tree traversal. Now how will you implement binary tree? We can implement binary tree using an array. So this is the rule for that. The root node will be stored in index 0. So root node which will be stored in index 0, and if root node is stored in I, if any node is stored in I, its left child will be stored in its left child will be in 2 into I plus 1th position, and its right child will be in 2 into I plus 2th position. So in this example X is the root, so X is stored in index 0. Okay, X is stored in index 0, then X is having two child nodes Y and Z. So where this Y and Z will store? So we have to find the index for Y and Z. So the left child is Y, which will be stored in 2 into I plus 1. So here the value of I is 0. So 2 into 0 plus 1, which is equal to 1. So Y will be stored in index 1, and the left child, right child will be stored in 2 into I plus 2 index position, which is equal to 2 into 0 plus 2, which is 2. So the Z will be stored in index 2. So like that we can store all the elements from the tree. Now we'll move on to binary search tree. Binary search tree is a type of binary tree where it satisfies a particular set of conditions. So what are the conditions? So these three are the conditions. If you are taking any node V in the binary search tree or BST, it should satisfy all these three conditions. First condition is V node's left child and all of its descendants have lower values than V value. So if you're taking a particular node V node's left child and all its descendants should be less than the value of V node's value. Second condition is the right child, V nodes, right child and all its descendants should have the value which is greater than the value of V node. That is second condition. And left and right subtrees must also be a binary search tree. So if these three conditions satisfies, we can call the binary tree as a binary search tree. So these are some examples for binary search trees. The first one is this one with root 8. So if you consider the values of the data in the nodes, so root is 8. If you consider all the descendants of the left child and all these descendant values, it is less than root. It is all the values are less than the root value, which is 8. And if you consider this right side, all the values which are greater than the root node. Okay, so this condition should be satisfied for a binary search tree. Then this is a binary search tree with a single node, and this is another binary search tree that also satisfying the conditions, because these all are left side nodes. So all these values are less than 10. So it's a binary tree. Now how will you create a binary tree? So we have been given with a set of array values. How will you create binary tree, or how will you insert these values into a binary search tree? That we will see. So first value is 50. So 50 is inserted as the root node. That is 50. Then the next value is 15, which is less than the root node. So according to the rule of binary search tree, this value should be greater than the left child. So 15 we can insert here. Next value is 75, which is greater than 50. So 75 will be inserted here. Next is 81. 81 is greater than 50, so definitely it will go to the right side, and to the right side of 75 it will get inserted. Next is 77. 77, which is lesser than 81, so it will be inserted as the left child of 81. Next is 30. 30 will come to the left part of the root, that is it will come here, and again it will be checking. Then 15, here it is 15. 30 is greater than 15, so it will be inserted here. Next 64, when 64 comes, it will go to the right side of the root node, and 64, which is less than 75, it will be inserted here. Next is 99. 99 will be going to the right side of 81. Then 18, it will go to the left side because it is less than 50, so it will come here, and 30 will be compared with 18, and 18 is less than 30, so it will be inserted in the left side. Next, finally 33, 3 will come. 3 is actually less than 15, so it will inserted here. And last 35 will come, that will be inserted to the right side of 30. So this is how we will construct the binary search tree. Now these are some operations in binary search tree. We can search for a particular element in the tree, then we can do insertion, we can delete the existing element, and again you can do tree traversal, same as that of binary tree traversal, in order, pre-order and post-order. Here one of the main property that is to be noted is that when you do the in-order traversal of a binary search tree, it will always give a sorted list of elements. So that is one of the important property of a binary search tree. Now we'll see some gate PYQs. So first question, the set tree represents various traversals over a binary tree. The set S represents the order of visiting the nodes during a traversal. So two sets of data has been given as T and S. So it is actually in order, pre-order and post-order traversals, and corresponding L, M, N is given. So we have to match and we have to finalize which is the matching pair. Okay, so we know in order means the order for visiting node is left, root and right. So this is clearly given here, the left subtree, node and right subtree. Next one is pre-order. Pre-order means the node, left subtree and right subtree. So that also be given as true. Then finally post order. Post order means left subtree, right subtree and the node. So that also is correct. So the correct option is option A, 1 to L, 2 to M and 3 to N. It matches. Second question, the height of a binary tree is the number of edges in the longest path from the root to a leaf in the tree. The maximum possible height of a full binary tree with 23 nodes is. So we have to find out the maximum height of a binary tree with 23 nodes. So we have to construct a tree which will cover the maximum height. And also it is mentioned that it's a full binary tree, which means that every internal node must have 2 child nodes. So we can construct the tree like this, which consists of 23 nodes. So if you count this one, there are 23 nodes. And every node is having 2 children, or it will be a leaf node. So it is satisfies the property of a full binary tree. So then how we will measure the height of the tree? So we can count the number of edges from root node to leaf node to get the height. So here it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are 11 edges. So the correct answer is 11. Next question, consider a binary tree T in which every node has either 0 or 2 children. Let n greater than 0 be the number of nodes in T. Which one of the following is the number of nodes in that have exactly 2 children? So here we have to formulate an equation. We have to find out an equation that matches this criteria. So first we will assume the number of nodes as 1. So when the number of node is 1, it will be like this, only one node, and the number of nodes with the 2 children are 0. There is no node with, there is no children at all. Okay. Now come to number of nodes as 3. So we can form 3 nodes like this. Here number of nodes with the 2 children is 1. Next one we'll try with 5 nodes. So there are 5 nodes. So here number of nodes with the 2 children are 2. One is this and the other one is this node. And finally 7 we are taking means it will look like this. So here number of nodes with the 2 children are 1, 2 and 3. So from this we can form an equation, or we can form a relationship. If there are n number of nodes, number of nodes with the 2 children will be n minus 1 divided by 2. So if n is 7, 7 minus 1 by 2, that is 3. That is the correct answer. Okay, so the answer is, the option is B, n minus 1 by 2. Next question, suppose the values 10, minus 4, 15, 30, 25, 60, 19 are inserted in the order into an initially empty binary search tree. Let T be the resulting binary search tree. The number of edges in the path from the node containing 19 to the root node of the T. So if you have to construct a binary search tree using these values, then we have to find out the distance to the node 90. So it can be constructed like this. So first value is 10. So 10 will be inserted as the root node. Second value is minus 4. It will go to the left side because it is smaller than 10. Then next 15 will go to the right side. So if you are splitting like this, to the 10 left side minus 4, 5 will come. Right side all the other values like 15, 30, 60, 20 and 19 will come. So we can insert like this. It satisfies the properties of binary search tree. Okay. Now we will find out the number of edges to 90 from the root node. So 1, 2, 3 and 4. So finally we are getting the answer as 4. Next question, which of the following statements are true for any binary search tree having n distinct integers? So first one is the maximum length of the path from root node to any other node is n minus 1. That is a true statement. This is a true statement. Second statement is an in-order traversal will always produce a sorted sequence of elements. That is one of the major property of binary search tree. That is also true. But the other two statements are not true. So the correct option is A and B. Next question, the pre-order traversal of a binary search tree is 15, 10, 12, 11, 20, 18, 16, 19. Which of one of the following is the post-order traversal of the tree? So first, with using this pre-order traversal, we have to construct the tree. Pre-order traversal means the root, left subtree and right subtree. So here the root is given as 15. The root is 15 and all the values which is less than 15 will come to the left side. All the values which is greater than 15 will go to the right side. So 10, 12 and 11 will be in left side. 20, 18, 16, 19 will go to the right side. So again you can construct this node as 10 will be the root. Then since 12 is greater than 10, it will go to the right side of 10. Now 11 which is less than 12, so it will go to the left side of 12. So this forms the left subtree. Now coming to right subtree, the root will be 20. Then next value is 18 which is less than, so it will go to left side. Next is 16. 16 is less than 18, so it will go to the left side of 18. And finally 19, it will go to the right side of 18. So this is the right subtree. So we can combine this, finally we will get this tree. So this is the tree where we have to find out the post-order traversal. So post-order traversal means left subtree, right subtree and finally the root node. So here the root node is 15. So you just check the option, this A and B immediately we can eliminate because 15 is not at all coming at the last. Then from option C and D we have to find out which is the correct option. So here they are asked for post-order traversal. So left node will come first. So the leftmost node is 11. So 11 will come first. So this will be the answer, option C. Next question, which of the following are correct in order traversal sequence of a binary search tree? So this is based on the important property of binary search tree where it is like when you do the in order traversal of a binary search tree, it will always produce a sorted list of elements which is in ascending order. So you have to just check which all are in ascending order is given. So option 1, 3, 5, 7, 8, 15, 19, 25. So it is given as in ascending order only. Second one is not in ascending order. Third one is also not in ascending order. Fourth one again it is in ascending order. So 1 and 4 are only in ascending order. So in order traversal will always give ascending order list of numbers. So option A is the correct answer, 1 and 4. Next question, what are the worst case complexities of insertion and deletion of a key in a binary search tree? So the answer is big theta of n for both insertion and deletion. Consider the following rooted tree with a vertex labeled P as the root. The order in which the nodes are visited during an in-order traversal. So we have to construct the in-order traversal of this particular tree. So in-order traversal means left node, then right node. So it starts with S. So it will start with S, that is the leftmost node. Then it will go to its root node Q. Then it will go to the root of the tree, that is P. So left subtree now completed and root also visited. Now we have to move on to the right subtree. So where the first node visited will be the left node T. Then the next node is the root of that T, that is R. Then next is W. then U, and finally the rightmost node called V. So that is option A is the correct answer. The height of a binary tree is the maximum number of edges in any root to leaf path. The maximum number of nodes in a binary tree of height h is, which is one of the property of that binary tree. Here the answer is option C, that is 2 power h plus 1 minus 1. Next, the following numbers are inserted into an empty binary search tree in the given order. What is the height of the binary search tree? So height is the maximum distance of a leaf node to the root node. So with these values we have to construct a tree like this. So since 10 is given first, it will form the root node. The next number is 1, which is lesser than 10, so it will come to left side. Next is 3, 3 is greater than 1, so it will be placed here to the right child as right child of 1. Next is 5, 5 is greater than 3, again it will be placed as the right child of 3. Then remaining values are greater than 10, so it will go to the right subtree. So that will be inserted there. Now the question is, what is the height of the binary search tree? So height of the binary search tree is 1, 2, 3. That is the maximum distance from root node to a leaf node. So option B is the correct answer, 3. Next, suppose the numbers 751836094 are inserted in that order into an initially empty binary search tree. The binary search tree uses the usual ordering of natural numbers. What is the in-order traversal sequence of resultant tree? Here actually we no need to consider the tree itself, because we are asked for in-order traversal. We know that in-order traversal will always give a sorted list of numbers. So we have to just sort this list. That is the in-order traversal of that particular binary search tree. So here we can say that A is not the sorted order, B is also not in sorted order, but C is sorted order. So this will be the correct answer, option C. Those are the sorted list of these elements, since it is an in-order traversal. So that's all. Today we have seen the basics of tree data structure, and we have solved some previous questions also. That's all for today. See you on next video. Thank you.